Hello everyone, welcome back. In this video, we'll be taking a look at ordered fields. We did fields before, now we're going to look at ordered fields. Well, what are ordered fields? Well, the formal definition of ordered field is an ordered field is a field with a subset P in the field satisfying these three additional axioms to the previous 9 axioms we already learned. The ordered field satisfies these additional 3 axioms. So the ordered field in total satisfies 12 axioms. So the 10th axiom it satisfies is order of addition, also denoted as OA. So for all elements xy in the subset of the field, x plus y is also in P. So visually, for example, if this is the field and this is P, if x and y is in P, then x plus y is also in P. And the same goes to order of multiplication. If x and y are in P, then x dot y is also in P. Now let's look at trichotomy, OT. Well, quite obviously, it satisfies 3 properties. It has 3 properties underneath it. So, the 12th axiom of the ordered field says that every element in the ordered field is only, I want you to know that it's only either in P or minus P. So, how I like to think about it is P is a subset. P is this subset is where all the positive numbers are. All the positive numbers, for example, 1, 2, 3, are all part of P. So, so if an element is in P, it is positive. If every element is either in P or in minus P or 0. So basically, what it is saying is every element is either positive or negative or it's 0. So no one element can do both these properties. It can only satisfy one of these properties. It's either positive, it's either negative, or it's 0. So that's what OT basically says. It says that when x is in P, then x is positive. If minus x is in P, then x is negative. Then if x equals to 0, then well, basically x is 0. So this is the most tricky one. Let me explain that. So it says if minus x is in P, then x is negative. So we have established before that all the elements in P are positive. So example, look at this element minus 3. So minus of minus 3 is in P. So minus of minus 3 is 3. So if minus of minus 3 is in P, that means minus 3 is negative. Now that's what basically this says. Now this minus 3 is an example of the second property of OT. So let's see why we need order. Why do we need order? We were we were well off with the fields, right? So let's take a bit of a look at why we need order, why we need ordered fields. Well, examples of ordered fields are the reals and the rationals. The reals and the rationals both satisfy the 12 properties of the ordered field. They satisfy the 9 properties of fields and also satisfy the 3 additional properties of ordered fields. So let's take a look at why we really need ordered fields. So if you remember from the previous video, this weird field, the even odd field, where there are only 2 elements. So if you consider 1, 2, 3, 4, then 5, and so on and so forth, 1, 3, and 5 all represent the same element, they represent odd, and 2 and 4 both also represent the same element, they represent even. So in this field, there's no order, right? When you go from 1 to 3, you're actually going back to 1, because it's the same thing. If you're going from 1 to 3 to 5, you're actually moving back to 3 to moving back to 1, because it's the same number. It's the same number they're representing. It's the same element they're representing. They're all representing the odd field. So if you go from 1 to 3 to 4 to 5, you're basically representing the same element. You're actually going in a circle. So there's no order in this field. So to do our calculus on the number system, we need a strong number system which has order. Well, the nine properties which we learned before, there were the nine axioms which we learned before that define the field. They were well and good, but we need more of a order to do our calculus and analysis on them. So that's why we need these three axioms, with these three additional axioms, specifically OA, OM, OT, order of addition, order of multiplication, and trichotomy, to add order to our number system. Since we're still in the process of building a new we're still in the process of building a number system. We'll be of building a number system so that we can do our calculus and analysis on that number system. So let's take a look at why the even odd field is not an ordered field. Let's do a formal proof of that. What we did was basically scratchy work. So let's give a formal proof of that. So we're going to do a proof by contradiction to prove that it's not an ordered field. Now this is, remember, this is the first proof of proof by contradiction we're doing in this course. So whenever we're doing a proof by contradiction, we assume the opposite. So in this case, suppose for contradiction, whenever you're doing a proof by contradiction, we always start this way. We always write suppose for contradiction. So suppose for contradiction, since we're assuming the opposite, whenever we do a proof by contradiction, we assume the opposite, and we hope that something odd or something strange or something contradicting ends up happening. So that's how a proof by contradiction basically works. So suppose for contradiction, the even odd field is ordered field. So let's see how we can go about this. So remember, we said P is where all the positives exist. So let P be the corresponding set of positives. So let's now focus on 0. So remember from the previous the 10th axiom, so the OA, which said if x and y is in P, then x plus y should also be in P, right? So let's see about the order field. So let's, for example, take odd. Let's focus on the element odd in this even odd field. So odd is in P, right? For example, 3 is odd number, 3 is in P, right? So let's focus on this. Odd is in P, but odd plus odd is equal to even. So for example, 3 plus 3 is equal to 6. So but remember that even is for example, 0 is an even number. There's a proof for this, but just assume that it's true. 0 is an even number. So OA says that if x and y is in P, then x plus y should also be in P. So if odd is in P, odd plus odd, so odd plus odd should also be in P. So but odd plus odd is even, and 0 is even. this shows that 0 is in P also. So this contradicts OT. OT basically told us that either element is in P, or negative x is in P, or x is 0. But this shows us that odd is in P, but odd plus odd, which is even, is in P, but even is in 0 too. Even is 0. So this something strange. This is a contradiction. So this contradicts OT. So this shows that our assumption that the field is ordered is wrong, because this is contradicting something strange is happening. So our assumption is wrong. So our assumption that our the even odd field is an ordered field is wrong. So this proves that the even odd field, this strange looking field, is not an ordered field. So that is the proof. So that is, sorry about that. So that is the proof that that's a formal proof of which shows that the even odd field is not an ordered field. So I hope you guys are getting this. I hope you understand the contradiction. Let's go over to one more time. So we are supposed to show that the even odd field is not an ordered field. So we're doing a proof by contradiction, where we assume that the even odd field is an ordered field. So whenever it's an ordered field, since we're assuming that it's an even odd field, we should also assume that the three axioms of the ordered field should be followed. So if odd is in P, then odd plus odd should also be in P. But odd plus odd is even, and 0 is even. So this is just basically a contradiction, because if odd is simply a P, and odd plus odd should also be in P, but odd plus odd is even, and 0 is even. This shows odd plus odd is 0. So it doesn't satisfy OT. This contradicts OT. Something strange is happening. So our assumption that the even odd field is ordered field is wrong.